All right, I thought I would give a handful of hints on this problem. It is super simple looking, right? There's like a concentrated moment and a force, and then a section or a sector of a circle, and you have equations for sectors of circles, right? You got, something like this area of circular sector, and you've got a centroid, some moment of inertia equations for it. And so it doesn't look like that big a deal. And on an exam, this one is probably more than what I would ask on the trigonometry, geometry side of things, because there's a lot going on. It's not stuff that you shouldn't be able to do. It's just you got to figure out some stuff with this geometry. If this problem had instead of a sector there, it had an I-beam or some other relatively regular cross section, then this would totally be exam type problem where you've got a pretty simple, assuming that the maximum moment is going to be at the wall for a cantilever beam. So you go and find that moment, do summation of moments about, that's point A, do summation of moments about point A, figure out what that moment is, and then plug that into your flexural stress equation. The difficult with this thing is this cross section. So let's just look at it for a little bit. Over here, I guess, somewhere. Where did I put it? There. So you have that sector, and you have some dimensions on it even. I don't know, something like, well, we can do better than that. So let's see which ones you know. You know C and D, so it's kind of width, if you want to call it that. And I think all the way to the top. Yeah. That. And they called it D. And then they had these points. They had a point here and here and here. And for this particular problem, it's asking you to find the stress at those different points. You know that the neutral axis is somewhere, maybe here. You can actually go, and you have to go, and use this equation, the one that's, x bar in this case, you just have to rotate it 90 degrees to make it the orientation of your sector. And you can figure out the location of that neutral axis, except that there's a little issue in that, let's see, where'd it go? Here's the equation, that alpha right there is not given, right? You don't know alpha. Alpha, remember in this one, in these equations, actually I think it's only the sector equations where an angle measure shows up, but those have to be in radians. So if you notice the denominator, the numerator has sine of alpha, so if you put sine of the degree measure, you'd end up with the right thing. But the denominator, you're just dividing by alpha, not anything sine of alpha or cosine of alpha, it's just alpha. And let's take a little tiny diversion over to y, radians, and degrees. So here's a circle, and it has a radius, r, and you can make an angle, we'll make it theta, that's also r, and 1 radian, so if that angle theta was 1 radian, it would mean that this distance here, that arc length, was also r. So a radian is this arc length over that radius. A radian has an actual meaning, or degrees. This circle, you know that the circle has 360 degrees in it, but the 360 doesn't mean anything. The 360 is a really convenient number because you can divide it by 12 and 5 and 2 and 10. All these different numbers divide evenly into 360. And so 360 is arbitrary. We could have picked 100 or 500 or 200 or whatever, but 360 is kind of an arbitrary assignment. So it doesn't have a meaning when it comes to these equations, where radian means the ratio of that arc length over the radius, and it has a meaning that's associated with the circle itself. And so equations that deal with angles a lot of times need radians in there, particularly in this case, because you've got this denominator. If you just put a randomly assigned number in the bottom for the angle measure, you know, maybe you didn't want to use degrees, maybe you want to use some made up unit of divisions for a circle. It doesn't mean anything in the equation anymore, but that alpha always means something because it relates to a ratio in all circles. So that's why whenever you see these equations that have angle measures in them, unless it's the sine of the angle or the cosine of the angle and you're going to get back to some other number anyway, then that number is going to be radians. So be sure you put radians in there. Also, in this particular one, be sure that you look at your picture and say that the angle they're talking about is really half of the sector's angle, right? Alpha is half of the total wedge here. But you're not given that. You know, you're given C and D. So you have to go in here and make some little triangles and figure out, all right, well, you can figure out the neutral axis. Well, no, because you need alpha. So you got to go figure out what is alpha by figuring out some of these information about the triangle here. You know, this is 1/2 of C. You know, this, I think, well, yeah, you know that this distance is D also, right? Because the height of this sector is shown as D, and that one that I labeled as D is just also a radius because it's a sector of a circle. If this was an ellipse or some other shape that wasn't a circle, then you wouldn't be able to make that piece of knowledge transfer over. But all of these lines that I drew, these are all radiuses. This is a radius of a circle. Now, I probably did not draw it very circular, but you know, if we were able to make a circle that's it wasn't too far off, except my center is really far off. You know, we did more like that, but that's okay. So these are all radius numbers of the sector, the little wedge shape. All of those lines that I drew are radius, so they're all D. So you know D, you know this is 1/2 of C for this half of this chord up here. And then you can calculate alpha. Once you calculate alpha, then you can find your neutral axis location using the equation from this sheet that we just looked at. Once you know the neutral axis, then you can start plugging into sigma equals m times y over I, and it wants you to find the moment of inertia. I think it labeled these C, E, and G. Oh wait, it's over here. D, E, and G. So D, E, and G. So each one of these, the difference would be they'd have the same moment of inertia, they'd have the same bending moment, they'd have different values for the distance from the neutral axis. So if you're calculating the stress at G, you put that distance in there, it would be G. If you want to know the stress at D, you go from the neutral axis down to here, and that's the number that you would put in for Y. And then for E, you go from the neutral axis up to here, and that number would be a little bit different. So they all have different flexural stress equations, even though they have the same I, same bending moment, but they're different distances from the neutral axis. And the way flexural stress works is the further you get from the neutral axis, the more stress and strain you deal with. So that would be why it's asking you for, it's actually asking you for 6 different things. It's asking you for 3 at one location in the beam. Remember this beam, it's asking you for 3 of them, kind of drawing here, 3 of them from point A, and then it asks for location of maximum positive bending moment, location of max negative bending moment. The negative bending moment maximum is at the wall, and then turns out that the maximum positive is at B, and that's where it goes, it's most positive. You would have to draw the shear and bending diagram to be sure of that, but you can kind of look at it and tell, but also that's that would be how you would know that where the maximum positive M and the maximum negative M are located. Negative M at A, most positive moment at B, and then different moments in between there. And then so you basically go back to your cross section, and well, not that one, you would have one number for M 3 times, one for point D, one for point E, one for point G, and then another set of those where you plug in the maximum positive bending moment or whatever. And so that problem is probably only beyond a test problem because of having to deal with the sector. It's not that far beyond a test problem, but I probably would never ask that as a test problem just because of the little bit of extra work you have to do to figure out. You got to find the neutral axis, you got to find some alpha to be able to deal with the neutral axis, and so there's a little bit of other work that's not really statics related. It's stuff you need to be able to do, but not stuff that I want to test on if you know statics or not. So don't be too afraid of that problem, thinking that it looks really simple. I'll probably ask it on an exam, and you need to know how to do it. All of that's true if this, the only thing, if I just gave you alpha, you know, or if I gave you theta, the whole angle there, then yeah, it's a test problem at that point. But one of the harder ones, but still, that would make it a test problem. Okay. Today, I don't want to save my changes. Today, what we want to do is we want to talk some more about beam deflection. Last time we talked about beam deflection more on the how did it come to be that we have these equations. These equations I posted, actually I have them here. I added this, I'll link to this site in Moodle, so you could go find them there on today's Moodle page. But it's just, these are standard. You can type in beam deflection equations and you can find hundreds of these charts that you could use. And they should, I didn't go check them, but they should be accurate as far as the equations that they present. And so we have all these. So at some point, someone has gone through, for each of these, there's usually 8. This one has 10, but there's 8 to 10 like generic beams. So this one has 5 cantilevers here at the top, and then 5 simply supported beams at the bottom. And they're kind of the generic things that you might encounter with a beam that has a single type of load on it. And so maybe a single point load, single distributed load, concentrated moment, you know, that kind of thing. And assuming that your beam that you're dealing with is exactly lined up with one of these, then you just take the equations and plug in the numbers. E is the modulus of elasticity of whatever this beam is made of. So it's steel, so it's like 30 million PSI. I is the moment of inertia for the cross section. So maybe it's one where you have to go calculate the moment of inertia, or maybe it's one where it's just a beam from a chart and you go look at the moment of inertia up out of the chart. P is the point load, or the W is the distributed load. And then L is the length of the beam usually in these. This one uses a lowercase l, sometimes they use an uppercase L. And then that usually gives you these 3 sets of things. One column gives you the slope at some point. It doesn't give you the slope as a function of x. Normally it gives you the slope at a single point on these beams. Normally, there might be some of these charts that give it as a function. Then it normally does give you the equation y of x. This one in the middle column here, it's they should be labeled y of x, but they're just labeled y. But there's an x variable in there, as you can kind of tell. Some of them have constraints on them, like that second row has 2 different equations for y of x. One for the span of the beam from 0 to the point load, and another one from the point load to the end of the beam, because the shape of that curve would be different. And then there's usually a column of like maximum deflection. So, because that's a lot of times what you're interested in is maximum deflection. So what we want to do is figure out how do we use these when we don't have one that matches one of these pictures. So, and I don't mean like it's mirrored. If it's mirrored, you can mentally work that out. But if it's a combination of things. So I want to work through maybe 3 of these that aren't exactly like the pictures. So one of them, let's do all 3 cantilever beams. So one of them could be something like this. That's case number 1 in the chart we were looking at. So that's a point load on the end of a cantilever beam. But let's add a distributed load all the way across the thing. So there's not one that's like this. There's 2 that are like this. One, I think case 1, and one that's case 3. Yeah, case 1, cantilever beam, concentrated load P at the free end, and case 3, cantilever beam, uniformly distributed load omega, newtons per meter. The units obviously don't really matter. There's nothing in this equation that have units tied to it. None of these constants or anything are tied to units. They're all tied to the process of getting the equation. So the units don't actually matter. They're just telling you that it should be labeled like force per distance or something, not specifically newtons per meter. All right. Let's put some units on this so we're not just making up stuff. Let's say that 1, 2, 3, 4, let's make that 7 feet. Good. And then let's make our point load 3 kips. So 3,000 pounds on the end of this. Let's make our distributed load 500 pounds per foot. And let's make our beam something. Do I still have the S stuff open? No. All right, so we'll have to get us a chart. Well, there it is right there. Let's use an S beam. Oh, I didn't want to save it. We are using, I'd said feet in there and kips and pounds and stuff, so let's use the US units for this one. Let's make it relatively small so it will deflect some. Now these equations for deflection, they don't tell you if the beam can actually do this. They just tell you, assuming that it doesn't deform permanently, it doesn't fracture or anything like that, this is how much it would deflect. So it's possible to calculate a number here, but the beam can't actually do that because it would break or something before it got there. So you have to be aware of that. Let's do S7 by 20. That's the one I want to do for some reason. So we need the moment of inertia really is all we need from here. We do have the XX and YY versions. I didn't say anything about this beam turned sideways, so let's assume I'm using XX, which is going to be this column. So we're going to need the very bottom of the screen, 42.4. These units are inches to the 4th power. So S7 by 20, 42.4 is our number. So S7 by 20, I equals 42.4 inches to the 4th. So that'll take care of that. Let's say that it's this some kind of steel, and we go look up steel, and E is 29 times 10 to the 6 psi. So that's just the modulus of elasticity out of a chart somewhere. The 20, the S7 by 20 does assume that this beam is steel. I couldn't just say it's S7 by 20, but then change it to aluminum, right? You wouldn't really make an aluminum beam, but there's different reasons for that. I guess you might have some little machine that has a part acting like a beam and it's in aluminum, but a building wouldn't have aluminum beams in it. Anyway, or, well, there could always be aluminum beams in some buildings, like a shed or something. Anyway, we have this number. We've gathered these numbers, however we managed to get them. On the exam, these are numbers you probably have to look up. So you have the little charts, and you have to go find I, find the material, and get E. So you look those numbers up. All right. Now what we want to know is we don't have a case that has a distributed load all the way to the beam, end of the beam, and a point load also at the end of the beam. So what we have to do is use a process called superposition. And superposition is not specific to beams and bending. It's in circuits and all kinds of other fields also. But the idea of it is that the cumulative effect of individual whatevers, in this case loads, is just the summation of all those effects. So you figure out what the point load does by itself, and you figure out what the distributed load does by itself, and you add them together. And that's all superposition is telling you is that you can add the effects of individual forces or individual whatever they might be. So we go and find, we simplify or change or however you want to think about it. This plus this and you just add them together, and that will be the same as what we originally drew. And we can do that. That's pretty simple. We just go, case number one says, well, we have to know what we're looking for. Let's say we want to find max delta, max deflection. So that's for this cantilever beam, maximum deflection is at the very end of the beam, right? So we even have shortcut equations over here that tell us maximum deflection for a point load at the end of a cantilever beam and maximum deflection for a distributed load all the way across a beam. So we just need those two equations, PL cubed over 3EI for this one, delta max for the point load, PL cubed over 3EI, and delta max for the distributed load, I don't remember, it's WL squared or omega L squared, L to the fourth over 8EI. Is that right? Didn't make a mistake. W L to the fourth over 8EI. Okay. Then all we have to do is make sure we count our units correctly. So P, the point load, is 3 kips. I should put that in as 3,000 pounds. L, you want to be careful. You really should go back to where you got that equation from and check what they're counting as L. And they have L shown as the whole length of the beam. That's L. Same thing on the distributed load. So it's the whole length of the beam. Sometimes it may not be, so you have to check. So for us, I made that 7 feet long. Oh, well, that's fine. I do want to keep my units in inches and pounds, so I'll do 12 inches per foot. And we have to cube that. 3 is just in the equation. E we looked up was 29 million psi, and I was 42.4 inches to the fourth. And then we can just calculate it. Let's see. 42.4 times 29 million times 3, and then 3,000 times 7 times 12 to the third power divided by that answer we just got. All right, so if I did it right, 0.482 inches. And, you know, that's half an inch, but where you put 3,000 pounds on the end of a 7-inch tall, 7-inch tall beam, I-beam, 7 foot long, that's at least a reasonable number. You know, it's hard to know exactly what to expect, but 400 inches would have probably said, no, that doesn't seem right. And a super tiny number like 0.0048 would have probably also been, I don't know. So half an inch kind of seems reasonable. This one, you have to be a tiny bit careful here. So W is 500 pounds per foot. And so it helps if you actually write out your units instead of just put the numbers in there, because what people will a lot of times do is, oh, I got to convert that over to inches, so I'll multiply by 12. But make sure you actually want to cancel out feet, so you divide by 12. W is the same as it was before. Well, I guess I just violated what I just said. Put your units down. It's raised to the fourth power this time. 8, same modulus of elasticity, and same moment of inertia. And we'll get some number there. So 500 divided by 12 times 7 times 12 raised to the 4th power divided by 8 divided by 29 million divided by 42.4. So I get a number in the same ballpark, 0.211 inches. So again, that's, reasonable number. I've got a total in this case of 3,500 pounds, but it's not all at the end of the beam, so I do expect it to be the same kind of scale, but a smaller deflection. So that makes sense in that range. Those look like numbers that I could believe. And then total delta max would equal delta max from the point load plus delta max from the distributed load equals, they're both pointing downwards, so maybe you would want negative signs on this, although these charts do indicate that y, a positive y, goes down if you look carefully at the diagrams that they give you. So that's why I'm going to keep them as positive. So we just need to add those 0.211 plus 0.482, 693. Now again, it doesn't mean that this will actually happen, because this doesn't say if the beam can handle this or not. If you want to know if the beam can handle that much, then you ought to check the shear stress. We haven't really checked shear stress at all, but you know how to check the flexural stress. For this one, you could do the flexural stress really quick. It'd be 3,000 times 7 feet. 3,000 times 7 times 12 to get it in inch pounds. Plus 3,500 times 3.5 times 12. That's our bending moment. We could use our section mod, this number, 12.1. So divide by 12.1. And so it says the flexural stress here is like 3,300 psi. The yield strength for steel starts around, 36,000 psi. So you'd be really close to yielding this beam to make it do this. So you'd have very little factor of safety. Your factor of safety would be like 1.2 or 1.01, or it wouldn't be a lot. I don't know what it would actually be. 36,000 divided by 1.01 or 1.09. So 1.1, you have a pretty low factor of safety, and that's normally not something you want for a design of this type with a beam. So you probably would redesign this to be a bigger beam or have less load on it or something else. Bigger meaning S9 or something like that. Okay, so that one's pretty straightforward. And that's the level of a simple version of this for a test problem, where you straight up take two cases and add them together. But there's other times when it's not quite that simple. So this one, now this one's going to seem a bit odd because the chart that I have pulled up right now actually has a case like this, but the one in your book doesn't. So this one is actually case 2 in this chart. It has a cantilever beam with a point load that's not at the end. And so it actually does have how you would handle this, but I want to show you what's going on here, because it doesn't have the next one we'll do. And it doesn't have the same thing here with a distributed load that doesn't end at the end of the beam, but ends somewhere in the middle of the beam. So there's a process that you can use when you have that sort of thing. And here's what would happen. All right, so you think about how this beam is going to bend. So it's going to, maybe start right here. Maybe this is the neutral axis. And we're going to exaggerate how much it bends, but it's curved right here. But this remainder part of the beam doesn't have any force. We're ignoring the self-weight of the beam. It is possible that the self-weight of the beam acts like a distributed load all the way across the thing, and we're ignoring that. In fact, I ignored that when I calculated the stress here. So it's very possible that when we put the self-weight of this beam in, that it would be over the yield strength of that steel. Anyway, ignoring the self-weight of the beam, then this last section of the beam is still deflects, but basically you have a slope right here, and it just continues in that direction. So what you do with this one is you treat this like a little beam with, and again, either include or don't include the self-weight. We're not going to include the self-weight. So you treat it as a little beam with a point load at the end, and then you calculate, delta max here, or Y max, since that's what they're calling the deflection in these equations, is Y. Then what you do is, for the rest of it, you treat this like a little triangle, and you calculate the slope at the end of the little beam, which that's this is just case 1, and you have the slope at the end of the beam, PL squared over 2EI. And it comes out in radians, so that number is PL squared over, was it 2EI? We'll look and see in a minute. Well, let's look now. Yes, PL squared over 2EI. So you know that that's the radians, and this side, or this side, because this is a really small angle, is, whatever length this is. And so this is B. You can also treat this as B if you wanted to. Since this is a really tiny angle measure, then what you can say for this height, the Y that you're trying to tack on to the end of the beam, is B times theta, as long as theta is in radians and really small. Because basically what you're doing is you're treating that like an arc length. So I drew it as a straight line, but you're treating it like a little arc length, like it's sweeping through that angle theta. And they're essentially the same when theta is a small angle measure. If you do, you can prove it to yourself. Tangent of a really small radian is basically that radian. Tangent of 0.01 is 0.01 in radians. So for this one, let's put some numbers. Let's use our same beam so we don't have to go look up new E and I values. So it's a S7 by 20. So let's so I is still 42.4 inches, and E is based on the modulus of elasticity for this made up steel. It was 42.4, right? Yes. Okay. And then let's put 5 kips, and let's make this 4 feet and this one 3 feet. What I labeled as B is 3 feet. So how you do this one is you do delta here. Let's call that delta. Well, let's use Y since they use Y in their equations. Y1, and this one will be, oops, Y2. Okay, so Y1 is equal to the max deflection for a cantilever beam with the point load at the end of it. The one thing you have to be careful here is that in this case, L is not, don't think of it as the total length of the beam, think of it as the distance between the support, the wall, and the point load P, which in our case is not the total length of the beam, it's only 4 feet. So PL cubed over 3EI, P, and well, we're right, L cubed over 3EI, but L equals 4 feet, not 7 feet. So P is, I made it 5,000 pounds. Like I said, L is 4 feet, so 48 inches, but we have to cube that. 329 million PSI and 42.4 inches to the fourth. And calculate that number. Calculator went off. 5,000 times 48 cubed divided by 3. Is it just 3, right? Yeah. Divided by 29 million, divided by 42.4. 0.15 inches. Now that number is only the deflection here. So it's not the total deflection at the end of the beam. To get the total deflection at the end of the beam, we need to add in that number. So that one we said was B, which is 3 feet, times theta. We don't know theta. So theta at the end of the beam, or end of the short beam, theta at 4 feet is, and we got to go look that equation up, PL squared over 2EI. PL squared over 2EI. So P is the 5,000 again. L is the 48 inches again, squared, over 29 million PSI and 42.4 inches to the fourth. So this should be unitless when I look at these units, because the other one had inches cubed, so it left me an extra inch in the numerator. This one is inches squared in the numerator, so everything cancels out and I have no units. So it's radians, yep. No, so this is theta here at the end of the 4 foot section. It'll also be theta at the end of that because it's this constant slope. But I want to figure out how much is the beam sloping at the end of 4 feet. And then I'm going to continue that slope for the rest of the beam to 3 feet. But if I put 3 in there, what that would mean would be, this equation is this. It's based on a cantilever beam with a point load on the end of it. And so it wouldn't make sense to put the 3 feet in there, because that would mean, that would kind of be like I had a load out here somehow. It wouldn't really work. What I'm going to try and do is have the cantilever beam 4 feet long, point load of 5,000 pounds on it, and then calculate the slope at the end of that beam. And then once I know that, then I can calculate this height here. But no, it's not the 3 feet. And that's why I wanted to do this one, because it's sometimes counterintuitive. You want to put a 3 in there or something, but I really want to treat this kind of like two separate, I don't know if this is a good way to think about it, but two separate pieces of a beam, one that's bending and one that's just angled, sloping downward. Because if you had a beam, there's not one out here, if you had a beam and you push somewhere in the middle of it, then the part you're pushing on between it and the wall, that part curves, but the rest of the beam is just straight. And so that's what I'm doing, is figuring out what's the rest of the beam slope, what angle is it at? I'm just going to calculate that angle in radians, and then I'm going to use that to basically solve the little triangle, this little triangle right here. I don't know what this number equals. Let's see. Oh, nope, that's the last number. 5,000 times 48 squared divided by 2 divided by 29 million divided by 42.4. So I get a tiny number, but this is radians, 0.00468 radians. That is this. So this is the last little 3 feet of the beam. So what I've got here is, I'm treating it like this. That is that angle. And I want to know that distance. And I know that this side, doesn't really matter which one, but This side is 3 feet. Or you might think of this side as 3 feet. I would actually think of, the way we're going to solve it is that it's 3 feet here, but it will work the same either way because of this small angle for theta. So y is equaling 3 feet times 12 inches per foot times 0.00468 radians, and that'll give me that side of the triangle. You might be better off thinking of that as an arc length. So that would be the same thing like this, where this is theta and this is 3 feet. You might rather think of it like that. And as long as theta is small, those two things are the same. There's no difference between them, but as long as theta is small, which it is, it's 0.00468. So let's see, 3 times 12 times 0.00468 is 0.168 inches. And that's on the same scale as what we had for the other piece, 0.158. So our total, Y total at the end of the beam is 0.15 from the point load plus 0.168, these are inches, um, 0.32, we'll leave 1/8 inches. So in the range of 3/8 or whatever of an inch for the total deflection, but you have to do it in 2 steps. Now this particular chart does give you a delta max for case 2, delta max. They've kind of combined them together already with that PA squared over 6EI 3L minus A. They are doing a similar thing. If you expand that out, then they've got a similar type of equations that we created. You can see the PL cubed over 3EI is in there, and then you can see but they have a little bit different, minus PA cubed over 6EI, so they have a little bit different version of how they got to that point. I don't know if you can tell. In fact, I think they drew it a little bit oddly. Yeah, I don't know if I would call that straight or not, but this section is, we're assuming, linear, and this section is nonlinear, it's curved. And they actually have, they might be they're not including the self weight of the beam because they don't have anything to help you include that, but they are doing something a little bit different than what we did. But we're saying that this, let's make it a different color. We're saying that that section, the red one, is a linear slope, whereas the section from the wall to the point load actually curves. Is how we're going to treat it. And that's how our web work does it. That's how we solve it on any of the exam problems. If that problem shows up, is we treat the red part as a linear slope, a constant slope, and we treat the constant slope is whatever it was at the end of that A section of the beam. And then they may or may not be doing that with this particular. So if you go try to do web work problems and you use this for one of these problems, I'm not certain it will give you the exact same answer as the process that we did here. This would work the exact same way if you had a beam like this. So cantilever, distributed load, it would be the same exact thing. You would use the case for a distributed load at the end of a beam, all the way to the end of a beam, and then you tack on this second part of the beam that's just a linear slope, and you would have all the necessary, like you know the slope at the end of the beam here for a distributed load, and you would treat that second section, the B section, the same way we did for a point load. This one would not work that way. Again, we'll do a cantilever. Oops, I want that to be a load. So this one, you could make a really quick approximation by lumping the distributed load and putting a point load there and doing what we just did, right? So you could do that. That's not exactly the best way to do it, but you could do this. That won't get you quite the same effect though, because if you lumped it with the point load where I show it, then that B section of the beam you would treat as linear, but it really has a distributed load across it, which is curving it. So that's not the best way to do that one, although it'd be a quick, if you just wanted a quick way to calculate it, that might be one way to do it. A better way to do that, and you have to think outside of the box to make this one work, is to do this. So cantilever beam, I'm not going to draw the whole beam, I'm just going to draw a line with a distributed load all the way across it. So, and let's just make them well, let's actually solve it, I guess. So this one will be, I don't know, 500 pounds per foot. That's what we used earlier. All right, so that at least accounts for some of it, but it overestimates it, right? Because I've got all this distributed load that between the wall and where my original distributed load started. So I had, maybe this is 4 feet. I'm going to make this one 5 just so we have two different numbers that we can track in the equations. So the 4 foot section really isn't supposed to have any distributed load, but the way I drew it here, there is some distributed load on it. So I need to add something to this one. So I need to add, let's do some more down here, this guy. I need to add actually a negative, or opposite, I'm going to draw it upwards, 500 pounds per foot. So now the two parts from the 4 foot sections from the wall to where my original distributed load started, I've got a 500 pound distributed load pushing down on that section, and I've got in my second thing I drew a 500 pounds per foot distributed load pushing up on that section. So those would cancel each other out. And so this one, the one I just drew, you would have to treat like this, which is just like this. If we're doing deflection at the end of the beam, which is what I assume we would do. So let's do that and call it a day. So the first one, that's really easy. In our chart, that's case 3. Deflection at the end of the beam, well, it says deflection max, which is at the end of the beam. It's even labeled over here, delta max. Hey, they are using delta. They just use Y over here. Okay. WL cubed over 8EI, or if that's omega, we can do that. So this one, delta max equals 500 pounds per foot. Convert those over to inch pound, or pounds per inch, times L to the 4th, which that L is the whole length of the distributed load, which is 9 feet. Convert that over. That's to the 4th over 8. Let's just use the same beam we've been using. So E is 29 times 10 to the 6 psi, and I is 42.4 inches to the 4th. And let's make sure that that's the actual right equation. Yes. Okay. So this will give us the deflection at the end of the beam if the 500 pounds per foot was over the entire beam, which it's not, but that's what it would give us. So 500 divided by, I guess I have divided by 12 and multiplied by, well, but that's 12 to the 4th, so I can't just do that. All right, so divided by 12 times 9 times 12 raised to the 4th power, divided by 8, divided by 29 million, divided by 42.4. So it says 0.576 inches. Again, that's a reasonable number. It's not at least out of complete scope of what's possible there. This one, I have to treat in two sections. So the first section is going to be just like the equation we did, except that this 500 pounds is pointing upwards. So it's actually pushing the beam back upwards, and I assigned deflections that push downwards as positive. So this is going to be a negative. So delta max for, I don't know, these are separate ones. So this section is negative 500 pounds per foot converted to pounds per inch times this section is only, this is only 4 feet. This section I made 5 feet. So times 4 feet. Let's just do 48 inches to the fourth. Same denominator though, 8 times 29 times 10 to the 6 psi times 42.4 inches to the fourth. So this deflection is going to be negative 500 divided by 12 times 48 to the fourth divided by 8 divided by 29 million divided by 42.4. So it's a small number. 0.0225 is what we'll round it off to. That is, I didn't draw this, but that's basically this number. So this little height right here is 0.2 or 0.0225. But now we've got to take into account that this beam continues sloping, and we've got to figure out this number. So we need to know theta at the end of the beam. These, these should be a continuous slope at that point. I kind of made them look discontinuous. So this one we need WL cubed over 6EI. So that's the slope at the end of a distributed load. WL cubed over 6EI. WL cubed over 6EI. And this was going to be sloping upwards, so maybe you think of this as a negative because they assigned sloping downwards as a positive. So W, 500 pounds per foot. I'm going to convert it over. 1 foot has 12 inches. L is only the 4 feet because I want to calculate, or 48 inches. I want to calculate the slope at the end of the 4 foot section. 629 million and 42.4 inches to the fourth moment of inertia, and it's going to be negative in our coordinate system. 500 divided by 12 times 48 to the third divided by 6 divided by 29 million divided by 42.4. All right, negative 0.000625 radians. Then, so that's, this angle measurement. This y that I need to know, y3, we'll call it, y3 equals theta that we just calculated times the 5 foot radius of this arc that we're making. So 5 feet, but I do want that in inches, so times 12 inches per foot. And it'll turn out negative because theta is making it shoot upwards. So negative this number times 5 times 12. So negative 0.0375 inches. So this, if I sum that, and that, I should have the total deflection at the end of the beam that looks like that, where the distributed load is shifted towards the end of the beam, but not towards the wall. So let's see, 0.576, I subtract off 0.0225, subtract off another 0.0375, and 516. So delta total equals 0.576 inches minus 0.0225 inches minus 0.0375 inches, which is 0.516 inches. And those numbers seem reasonable. You should, check them. There's lots of little places where you put a number in a calculator wrong or something like that, and potential to make errors. On an exam, this, not necessarily this exact problem, but this would be about as much as I would ask if this is one of the harder ones, where you have to do 3 different things. Take one case or take 3 different cases or whatever. If it's the average level, then I'm not going to ask you to do quite this much, just because it's so time consuming to calculate all the little numbers, and you don't have that much time on an exam. WebWork's going to have you do all kinds of crazy ones, so you'll get plenty of practice with the really complicated sets there. So on the exam, don't be too worried. But these are not on exam 2. These are exam 3 also. Yeah. There is a quiz 4. I'll have to see if it needs to be before the exam or not. I'm not sure what content's on it. Yeah, I'll look and see if it makes sense for exam 2 or not, because I don't remember what's on it. Beam deflection is not on exam 2 at all. Beam design is the last thing we covered. Homework 21. Oh, they're out of, okay, all right. A sphere. Which problem? Oh, wow, okay, we haven't done that yet. Okay, so maybe that's not the best one for next. We'll do that soon, but I'll reassign its due date, because that, yeah. The others made sense though? Oh, okay. Right. Yeah, that's not the next problem set we need to do.